Okay, good afternoon, everyone. So welcome to this electronics webinar. My name is Tisa. I'm a marketing officer at Infinite Simulation Systems. I'm going to be a moderator of this event, but let's wait just 1 or 2 more minutes for others to join. And then I will give you some instructions on how to use the GoToWebinar tool. And after that, I will give the word to the main speakers. So just let's wait 1 more minute. Okay, so let's begin. Before we start, I would just like to give you some instructions and share with you some additional information. Please note that this webinar is being recorded. The recording is gonna be shared with you after the webinar. And it will last approximately 1 hour. As you can see on the slide, you have some options. For example, you have expand your tabs, raise the hand. You cannot unmute yourself. You're all muted during this webinar. If you have a question, please, instead of raising your hand, ask a question under the bottom that you see in the screen, under the questions button, and all the questions are going to be answered at the end of this webinar. So again, don't raise your hand, instead put your question under the questions tab. In case we run out of time and there is going to be too many questions, we won't ignore them. We will just reply on them via email, and you will receive it together with this recording and the slides of this presentation. So today I'm joined by 2 colleagues, Edwin and Odysseus. So looking at the agenda, they are going to tell you more about electronic simulation and even give you some real life examples. But first, we will start with a short introduction of Infinite and ANSYS. So now I'm giving the word to my colleague, Edwin. Edwin, you're muted.
Yeah, thank you, Tisa. Thank you, Tisa, for the introduction for the webinar Electronic Design. I will first start to introduce myself a bit. My background is industrial engineering. I'm working for Infinite like 25 years, so some while now. Yeah, the first thing to mention and give some bit of background of Infinite as a company. I'm not sure you already are familiar with Infinite, but what we are the elite channel partner of ANSYS, doing this already for over 30 years now. And part of being the channel partner is also doing the support for ANSYS in the Benelux. That can be software installation and configuration, but also get more in contact regarding the things you want to perform. So we have a number of experts on all types of fields. So to support you, also we can organize trainings for you, also on site or regular trainings at our office. And the final goal probably of yourself and also of us, is to improve your design efficiency by using the ANSYS solutions. ANSYS itself is already for 50 years on the market. They are the industry leader, so it's the most used simulation software out there. And the only thing ANSYS does is simulation. So they are focused on improving the software year after year. And that also makes it possible to have a great, unique positioning for growth and new technologies in the future. Next thing is, if you look at simulation in general, then over here you can see that most of the times it starts with an idea and then with an early design, and that's also where the most of the costs are located. So using ANSYS upfront can help you to deduct the costs, and that can be by reducing the development time during your design and analysis, but also, of course, to avoid warranty costs. So that's the design and analysis part. Also, ANSYS is getting more active on the manufacturing part, for instance, reducing weight by doing topology optimizations, but also using ANSYS to simulate the 3D printing process, and especially for metal. And finally, if your product or process is in place, you can also do simulations. And the main reason is to reduce your maintenance costs. And that's what we are calling a digital twin nowadays. Over here you see an example of such a digital twin. This is an example of ABB. They are developing, in this case, an electromotor, and they want, the demands nowadays are getting more strict. And you have a smaller volume, and you have to still have the same cooling. So you want to optimize this, and in this case, the electromotor is calculated by Fluent to predict the thermal performance. Of this total model, there is a reduced order model built, and that's done by doing a couple of hard designs, and then out of these hard designs create a reduced order model so that you can have accurate answers in a matter of milliseconds even. And so that's done by this technique. And in this example, you see an electromotor, and you want to investigate the thermal behavior in, when such a train starts, when it accelerates, when it's in the cruise phase, and when it stops. And then you can decide from what's the temperature distribution to predict the motor failure real time. So the motor is censored, and you compare it with your simulation results, and you can decide on a very short manner what to do when things have to be maintained or the train has to be stopped. If you look nowadays at the ANSYS portfolio, ANSYS started a bit like a structure mechanical software, but nowadays you have special solutions for material investigations, for safety analysis, for doing structure mechanical. Also, LS-DYNA is part of the ANSYS family. For explicit calculations, fluids with Fluent, the most used coast. But today we are going to focus more on the electronics, and I think especially on the high frequency electronics. If you look worldwide in the high-tech industry, probably where your company also is, we have a lot of customers. So 97% of the Fortune top 500 uses ANSYS. We have also a lot of customers served in the semiconductor market, the smartphone, the telecom market, and so on. A lot of startup companies who start with new technology, and we want to have a special program to make it possible for them to start with the software. And we are in many countries active. You see some companies as an example, if we like NXP, and if we focus a bit down on the Benelux as a customer, for instance, using also ANSYS and our electronic solutions, and the high frequency solutions are, for instance, Nexperia, ASML, Thales, Thermo Fisher, Philips. So those are a couple, but there are many more. Now, one of our customers is Qualcomm, and here you see a smartphone example. Smartphones getting more and more complicated, but you still want to predict what will happen if you also look to the temperature distribution due to electrical loading. And these examples let you make the right decisions upfront and deduce the risk on warranty costs. Now I pass over to Odi, and he will go more in detail regarding the electromagnetic solutions. Odi, the floor is yours.
Thank you, Edwin, and thank you, Tisa. I hope everybody can see me and hear me well. Welcome, everybody. My name is Odysseas Votsis. My background is in electromagnetics. I have obtained my master's degree here in the Netherlands in the Technical University of Eindhoven. And I was working as an RF engineer prior. I have joined ANSYS and Infinite, not ANSYS, I'm sorry. I have joined Infinite 6 months ago, and as a specialization on high frequency electronics simulation. Today, I will be trying to talk to you a little bit about the state of simulation today and the many benefits that your company can have by using simulation very early on in the design process as a tool that can help innovate. So without further ado, let's see. Oh, sorry. Yes, sorry. Why we need the simulation software today? With the simulation, we can mimic the behavior of an object and or phenomenon virtually, and we can do this in an efficient manner. We can render a virtual testing environment which will significantly reduce costs. We can understand design tolerances and sensitivities by using simulation. For example, how does the design change to the thickness of a specific PCB layer? Maybe if it's not too sensitive, we can use a cheaper material to accomplish our design goals. Only simulation can provide these answers early on, economically, and easily. Now, traditionally, companies have used a design cycle of design, building, testing, breaking, and fixing the problem. Of course, such an approach can be expensive and time-consuming. Design rules and best practices may not give engineers enough guidance to properly design modern, cutting-edge products. By using simulation, virtual model prototypes can be created and simulated, giving engineers more freedom to tweak their design, to see how their designs will change. This helps engineers have a better insight of the design, but also it can give a higher degree of confidence to the physical tests that will be run later on in the circle to be successful. So these physical tests can be successful. Now let's see some of our customers, what they're saying. Of course, we have improved speeds. We've got creation model time greatly by using simulation. We can identify risks of failure very early in the design and see how we can accommodate for those. We can accurately see and optimize reliability so we can have a more lifelong product. But of course, it's not only this. We are also supporting everybody, and we are partners along with our expert consulting. We can help you and guide you through your workflow for better efficiency and design for excellence. Now, a wide range of customers have benefited from ANSYS electronic solutions. Benefits typically include reduced design and development phase, reduced material costs, also having fewer board redesigns and getting to the market sooner. we can have improved product performance and reliability. We have a number of assets such as case studies, white papers that show how others have benefited from ANSYS solutions. If simulation is used as a design tool early in the development process, it can greatly benefit and cut costs. Here in the graph, you can see that with a traditional approach, we can start seeing problems when the first prototypes are there. This can be a very costly thing in the design cycle, 100% more costly, 100-fold, sorry, more costly than if we have seen these problems in the initial concept. If we see problems even later in the design process, the costs rise exponentially, and it can be very detrimental for us. Working with simulation tools early in the design phase, engineers can predict issues and work on solutions or changes quickly without the need to physical test. Of course, they can design in such a way that it's also shielded later on in the development phase, so our product can be shielded from potential issues that might arise, which again will have detrimental cost in that time on the development phase. And of course, this goes hand in hand with the market trends of today. We have seen consumption and cost of electricity rising over the past decades. Efficiency is getting more and more important aspect of any electrical design, whether that is a chip, an electric motor, an antenna, anything. Being able to push boundaries to have increasingly higher efficiency, smaller footprints, and better durability is key in today's world. But in order to push those boundaries, engineers must have tools to allow them to innovate. Another trend of today is that more devices are being electrified in today's world. New challenges arise with this, such as durability, safety, and thermal management. We see that in order to tackle these problems and these challenges, 75% of executives are increasing virtual prototyping. Let's now take a look at the core innovations of ANSYS in electronic simulation. Electronic simulation today in electronics today we can simulate a lot of different aspects, from chip level to antennas to co-site simulation or even simulation of large-scale platform interaction. We can see here we have simulated a helicopter with an antenna on a boat, and we can see the fields generated from this interaction. Also, we can even simulate electrical strikes that might happen. As you can see, we have tools that any electronics can be simulated, any electronic system can be simulated in today's world. Here are all our EBU products catered towards different challenges in electronic design. Unfortunately, I don't have the time to talk about all of them, but I will try to give you a good overview of the capabilities of simulation today. I will also be talking mainly about high-frequency simulation with HFSS, HIWAVE, IcePack, and Sherlock being part of my portfolio. Of course, for the rest of the products, we can have a on-and-on discussion, one-on-one discussion, and we can help you understand what you can achieve or what your business can achieve with the help of these products. Now, one of the core innovations in all electronic simulation tools that ANSYS has is the automatic adaptive meshing. The mesh of the design is automatically created according to design constraints such as geometry or materials used. But more importantly, it takes into account electromagnetic propagation phenomenon, for example, hard turns and ports. In these difficult scenarios, the mesh will be denser. The mesh is essentially what is solved in the simulation. And that's why by having an accurate and correct mesh can be the key to success. This technology is the golden standard of accuracy and what allows ANSYS to be the leader in simulation. As you can see in the animation, the mesh is getting denser and denser with each pass. And you can see that the denser it gets, not only in specific areas, not in all areas. And this is accounted from the software itself, in which areas it will become more dense or less dense. And of course, this takes into account all the electromagnetic analysis that the software has done before. As you can see, with each pass and with the denser mesh we get better and more accurate results. For this antenna here, we can see initially with the mesh that the operating frequencies seem to be in a lower gigahertz range, but the denser we get the mesh, we can see the true performance of the antenna. Now, how does exactly this adaptive mesh framework work? Basically, it's an iterative process. The software is solving the mesh and it's seeing if the convergence criteria are satisfied. This convergence criteria can, of course, be set from the user, and it can be either very loose or very strict. The denser the mesh, then the mesh gets denser with each pass until the convergence criteria are satisfied. Of course, the denser the mesh gets, the more accurate results we will have, at the cost, though, of time and computational power. This convergence criteria can be fully customized, as I said. So an engineer looking to get a quick insight might choose for looser criteria to get faster results. But if we want a very detailed analysis of the problem, we might choose stricter conversion criteria as to have the best accuracy. The core idea of the technology is to provide the highest amount of accuracy with the least amount of computational power. So hence, we will have a minimal mesh. And as I said, all this is done automatically by the software. There is no need for the user input except for the convergence criteria. Now, how are we different from other engineering software? As I said, the mesh is key for accurate results. Without a correct mesh, all results are at jeopardy. Having a user-based mesh creation, such as other tools are using, is a very time-consuming aspect that then can also lead to the discrepancies of results between users, because one user might have created a different mesh from another user and have different results. This method of meshing can have a lot of challenges when it comes to small and curved geometry, which is usually key to solving electromagnetic problems. On the other hand, with the automatic adaptive mesh, the user does not need to spend, first of all, time to build the mesh, but second of all, also worry if his mesh is accurate or not. And he can be sure that the results he's getting are completely accurate with this automatic process. Also, this process, as I said, this automatic process can take into account more tricky geometries such as curves. And of course, you will not have any discrepancies between users. Now, simulation can not only help with minimizing warranty costs or test and measurement costs, or even reducing the number of physical prototype builds. Most importantly, it can provide insight about the design to the engineer. Which are the critical aspects of the design? Which materials should be used in this design? How can the design accommodate for signal and power integrity and complying with EMI and EMC standards? By using simulation, engineers also have extra insight which cannot be found via test and measurement, such as visualization of currents and fields, which is essential in electromagnetics to fully understand how devices operate. With digital prototyping, users now have the intuition to build better products by having the information and data they need quickly and easily available to them. Now, the main flagship product of high-frequency electromagnetic simulation of ANSYS is the ANSYS HFSS tool. ANSYS HFSS is a full 3D electromagnetic frequency domain solver. And with that, it can cover the most broad range of applications. This can be either filters, PCBs, RF components, antennas, even biomedical applications, and even automotive applications can be custom tailored with HFSS with great accuracy and insight. As I said, it's a very diverse tool that is used for all sorts of electronics applications. Here you can see some examples of this, where it can be used for car autonomy, or antenna placement, or even biocompatibility. All these models are generated in HFSS, and the domains and the applications that HFSS can help with is tremendous. Now, HFSS can solve the biggest and the smallest problems in electronics. And this is due to its diverse solvers, which all come with the software. Each solver is used for different problems. There is the finite elements solver for modeling high-frequency structures with high geometric and material complexity. This can be up to tens of wavelengths in electrical size. There is also the fast methods of moments integral equation solver, which can also expand the electrical size up to hundreds of wavelengths. We also have the shooting bouncing ray solver, which is the industry best-in-class technology for modeling installed antenna systems. We can go up to hundreds or even thousands of wavelengths in size with this. And of course, with today's increased computational power, HFSS is able to tackle even the most complex and large structures such as aeroplanes or cities. I will talk a little bit about this domain decomposition method later on in my presentation. So HFSS, as we see, is a high-frequency electromagnetic tool, analysis tool, capable of modeling from sub-wavelength sizes through tens of thousands of wavelengths, all in one environment with one integrated workflow. So you can see how flexible it is. However, in today's world, PCBs are very, very, very important, and they are in almost all electronic devices. When it comes to PCBs, a full 3D solver such as HFSS could not be optimal. That's why we have a different tool in ANSYS, SiWave, which is a 2.5D solver that uses the knowledge of how PCBs are manufactured to greatly simplify the solving of these extremely complex devices. This, of course, greatly improves computational time. What could be days in a 3D environment, in the 3D environment of HFSS, can be maybe solved multiple times within a workday with SiWave. SiWave can be used to see the voltage, current, and power distribution on the board and take into account signal and power integrity issues. It can also provide EMI, impedance, and crosstalk scanning across the PCB, but also act as a virtual compliance tool. It enables us to determine if the design will pass or will fail EMI or EMC standards, as well as communication protocol standards. By generating eye diagrams, we can be certain that our communication protocol standard can be passed. We can also see excessive current layouts and take into account this for our further design and how to further improve this. The two tools, HFSS and SiWave, are also integrated with each other. We can perform design iteration and tweaks with the SiWave engine, and then use the HFSS solver to act as a validation frontend for a more detailed solve of the PCB. Excuse me. We see here how the solving time is affected by using only SiWave or using HFSS. Of course, with HFSS being a 3D solver, it will take a much longer time to solve the issue, the problem. But only using SiWave might be less computational time. However, we might have a little bit less of accuracy. So by bridging together SiWave and HFSS, we can have the good of both worlds. Both simulation time is low, but also accuracy is very high. Let's take now a look at an example of this system integration. In a PCB board, we want to minimize, of course, coupling and interference between channels. At the same time, we want to have signal immunity as well as reliable channel capacity. But of course, we also have to have the board pass EMI and EMC compliance tests. All of these are very complicated issues. By using SI wave, we can very quickly and accurately predict the electromagnetic interference margins and see the crosstalk between the channels. We can also very easily scan the PCB for certain design violations or CI diagrams to see if our communication protocol compliance will pass. Then we can take these results generated on SI wave and feed them to our 3D solver, HFSS. We can then have a full 3D wave simulation of the complete system in order to ensure, for example, EMC certification test can be passed. Here you can see how the fields are operating in this 3D environment with shields, unshielded, and with partial shields. And the engineer can choose which is the best option, whether it's in terms of cost or in terms of ease of use. This workflow ensures that we can evaluate the effectiveness of the board in an early design stage and deliver with certainty a compliant product. Thus, we can have a cost-optimized, EMC-compliant product faster in the market by using these two tools together and by integrating these systems. Now, give me a second, I will drink some water. Another major concern for engineers is design for reliability. Engineers nowadays have to take into account thermal aspects, mechanical aspects in their design as to prolong, first of all, also the product lifetime, but also to be sure and certain that there won't be failures due to these mechanical or thermal constraints. Now, chip package, board, and even system-level thermal simulation is needed in today's market. We all know that devices operate better when they are within their thermal limits. And when these limits are exceeded, not only performance is degraded, but there is also a high probability of failure, which can be detrimental for our company. With identifying areas of heat generation on the initial design of the device, we can ensure good operation and safety. Thermal issues are usually accounted for quite late in the traditional design process, but can be very, very costly if they appear. Taking into account heating issues from the beginning can save us on both costs and time later on. This way, we can avoid the burn traces that we have seen in many, many PCBs, or even starvation of flow due to poor cooling in boards. IcePack is a tool of thermal simulation which can tackle these very serious issues early on. It has a computational fluid dynamics or CFD solver. IcePack can help accurately model any environment and domain, from the chip to the IC package to the supercomputer server room. IcePack can analyze this and can generate the heat maps that will be needed in order to better understand the design. Now, here are some examples of temperature mapping with IcePack in various applications. As you can see, it can be temperature mapping of a LED bulb or a heat-sink fan assembly, or even a supercomputer, as I mentioned earlier. Traces in the PCB, the thermal conductivity map of the PCB, or even animation of velocity vectors around a drone model. IcePack has an answer for a lot of applications. Now, IcePack, while being the very powerful CFD solver tool, also has a very good connection with other ANSYS tools. It generates the thermal network on the chip level. It consumes the electric and ohmic losses from different electromagnetic simulation tools such as HFSS and SI wave. Once it generates the thermal maps, it can also send to ANSYS Mechanical or Sherlock, that I will talk about a little bit later, or even generate a reduced order model to be used with system tools such as ANSYS Twin Builder that Edwin talked about. This reduced order model can also be used with third-party tools such as MATLAB Simulink. IcePack has coupling towards the finite element method tools, the electromagnetic tools, the CFD tools, and eventually passes results to the system level connections for system response. There is a comprehensive multi-physics analysis between all of these tools that works seamlessly. Now, along with thermal simulation, a lot of times mechanical reliability plays a huge role in the success of a product. With ANSYS simulations tools, we can simulate for possible shock and vibration, or have some drop tests, or even see the moisture effects of or we can also see the solder reflow of a PCB or the fatigue and fracture on the solder balls that will happen. So let's put everything together in this simple PCB example. We have the electrical analysis coming, getting us the electric losses of the board. Once we have this information, we can simulate the thermal map. Once we know the thermal distribution and the thermal expansion, we can further investigate possible thermal stress on a PCB, or even possible deformations on this PCB, or deformations in the solder balls of the board, and what effect will the heat have on them. So you can see it's an equilibrium here, and we have to work, everything has to work together in order to fully understand all the aspects of the design of the board. Now, as I was talking earlier, with optimization taking a center stage in today's market trends, we can see why a multi-physics analysis approach is essential. This detailed analysis is key to understanding the whole system and really strive and design for excellence. A lot of time consumers don't use multi-physics, but know they might need it in the future to better optimize their products, to follow with the competition. For example, thermal issues might not be still a case for some designs, but clients have seen that in the future, like after 2-3 years, these thermal issues start to arise with some of their products. So they needed to accommodate for that early in the design process before getting this product to market. Now, let's see a reliability example of a smartphone. As we know, in smartphones, we tend to increase electronic density as much as possible to fit more components in a small area. This packed density, of course, can lead not only to electromagnetic interference issues, but also overheating or mechanical stress issues if not designed properly. At the same time, electronics lifetime as well as prediction of failure has to be taken into account before designing the smartphone. With an accurate 3D multiphysics modeling, we can safely predict for all of this prior to any physical test. We can see possible performance degradation due to temperature, like here in this antenna. You see that the performance of the antenna at 25 degrees seems optimal, but if we have a heater environment, then the antenna performance degrades, and this will be detrimental for our design. We can also identify hotspots that could cause massive heat dissipation, something which can further lead to PCB degradation with warpage or even components getting out due to excessive heat. Simulating in this multiphysics fashion can help with the predictability of all the smartphone components. This helps extend not only the lifetime cycles, but also helps engineers to think outside of the box and add capabilities into the future, into the next design. Now let's take a step further, and we can also add reliability physics analysis to extract the lifetime of a PCB. Sherlock is a tool that does that. It's a dedicated finite element analysis tool that can analyze the various vibration fatigues, thermal cycling fatigues, or even solder reflow failures throughout time. So by implementing this reliability assessment early on can be very beneficial. Serloq can help in the initial part selection, because which part will have a better life cycle time, or which part on the PCB board might degrade faster over time. We can see this. Of course, also part placement plays a big role in the lifetime of a PCB. By assessing different topologies via Serloq, you can find the best position for the parts. Some components might be stressed due to physical vibrations over time, so a different placement can help overcome such issues. With keeping a design for reliability mindset, Serloq helps with the bill of materials of the board and the final layout, so we can be certain about the life cycle of our board. With Serloq, we can do various simulations to figure out the most optimal time to failure. We can move a component. So here we have moved this chip on a different location and see how this affects the curve of lifetime. We can add maybe some additional supports and see how that influences the lifetime of the product. Or maybe add a underfill. For this example here, we see that by moving the chip to a different position, it gives us the best time to failure and the least possible stress on our side that the product will fail in the future in its lifetime. Now to summarize, with different ANSYS tools which are combined in a comprehensive multiphysics solution, we can greatly predict all possible outcomes of a design. We can simulate for all possible scenarios and predict each aspect of the design, whether that is electrical, thermal, mechanical, or life cycle predictions. The ANSYS portfolio offers solutions for everything in a complete package. All of these intricate solutions of simulation can help engineers tremendously. By using it early in the design process, it can help them better understand the nature of the design and its flaws, safely predict any issues that might arise in all of the development phase, take into account every little detail. It can help them innovate and be ahead of competition. And simulation, as I said today, can tackle all possible geometries and sizes with the help of the ever-increasing computational power that we have at our hands, at our disposal. What was a time-consuming problem in the past nowadays can be solved in seconds, Simulator has developed and scaled over the years in both complexity and size, and is becoming a necessity in today's complicated world. With the help of high-power computing, or HPC, we are able to achieve faster and faster results and tackle even the most complicated and massive designs. 30 years ago, a simple coax to waveguide transitions might take hours to solve. Today, this is done in seconds, and we have computational power to thank for this. But also, ANSYS is always trying to innovate into that domain as well. So for example, as I talked a little bit earlier about the HFSS domain decomposition method, is taking part from these developments in computational power. Nowadays, we have multiple GPU cores in our PCs. So with this method, what it does is it slices the whole design into smaller parts, and the smaller parts are analyzed with a different core from the multiple cores that we have on our PC. This produces a result much faster than one single big simulation. Of course, these results are always following the golden standard of ANSYS accuracy. Now, ANSYS and Infinite are not only offering the tools, though, but they also offer a high-quality support along the way to help you develop your workflow efficiently. We help you develop your product life roadmap as well, looking along with you how to achieve design for excellency is our goal. Now here is an overview of different products. I will not stay too much into detail for this, since I know that the slides will be distributed to all of you and you can have a closer look to them on your time. Also, I think Edwin will be the best candidate to explain to you this solution product matrix. And now I would like to finish up with a very nice example from a partner that strives for the digitization of the automotive industry. As you can see here, we have a digital model for a full EMC testing facility done by Mercedes-Benz. You can see that the time for simulation today and what simulation can achieve and how it can help you is becoming a more and more necessary tool. Thank you all for your time. We will have now some time to go to the Q&A. I will give the control over to Tisa. Tisa, can you? Yeah.
I'm here. So thank you, Odysseus, and thank you, Edwin. Thank you for this presentation. Meanwhile, we received 2 questions from Ruben coming from the Kimo company. But since questions are quite long, including some sub questions as well, I suggest, Ruben, that I just unmute you and you ask Odi and Edwin yourself. So please, you have the word. Just make sure you unmute yourself, because I cannot do it for you only.
Hello, good afternoon. Thank you for taking my my questions. Can you hear me?
Yes, we can hear you, Ruben.
Okay, so we usually work with Altium to make PCBs, not RF-based, just mostly controller-based applications. If we want to use some of your electronic softwares or electronic simulation softwares to do, for instance, EMI, EMC testing, what are the inputs? I understand we can just import, I suppose, the Gerbers or the Altium project files, but do you need, for instance, model files like SPICE simulations for each IC? Do you simulate whole circuit? I mean, how do you set up the boundary conditions, and how do you set up the inputs? That's my first question. Thank you.
Yes, I think, yeah, as you said, we have basically, we are also quite good partners with Altium, and if I know correctly, Altium has a built-in plugin for exporting EDB files, for example, and of course Gerber files are also able to be accessed to the SI Wave software. And yeah, as I said, we do have this built-in plugin with Altium. And yeah, basically what you can do is for EMI or EMC analysis, you can have a full circuit simulation as well as you know, you can also apply an incident wave that hits the PCB and then calculate the induced voltages, for example, and currents of the ports that you have set up. So you can have this susceptibility analysis, or you can conduct emission reports, and of course, as I said, you can also couple these with HFSS for also a 3D full wave simulation.
Okay, did this answer your question, Ruben?
Yes, the only extra question I have on that is, for instance, for the IC, the integrated, the logic inside, do you need models for that, and how do they become available?
Can you please elaborate a bit? What do you mean by models?
For instance, if you want to simulate a circuit using LT-SPICE, you need, for your integrated circuit, you need an LT-SPICE model. Is that included in
Yes. like
end.
there is also like a full library of components in SIWave from different manufacturers that you can set up yourself, or you can also make your own components there.
Okay, so you provide that. Okay,
Yeah.
yes, so that's a question.
Yeah.
And the second question I had was, are there GPU solvers available? And if yes, how do they speed up?
The GPU solvers are available. I'm not exactly sure how many cores you can use by the get-go. I believe it's 4, but maybe Edwin can correct me on this. And
yeah, by default it's 4. And regarding your last topic, there are all kinds of eCat readers available also in all electronic products. So you can communicate already with work you've done in your electrical designer package. So you don't have to do the double work.
Okay, thank you.
Thank you for the questions. Okay, since there is no one else who asked anything in the chat, I would like to thank again to Odysseus and Edwin and to everyone that joined this webinar. As I said before, everyone will receive an email including this recording and the presentation slides. So expect that at the end of this week. But for now, I wish you a great day ahead, and hopefully we see you next time. So thank you.
Yeah, thank you all for attending, and feel free to ask questions after this meeting.
yeah, thank you all for attending. And yeah, I have also included our emails, so you can always contact us for more questions.
Exactly. Thank you again, everyone, and bye-bye.
Bye.
Bye-bye.